This is the first video in the chapter about acids and bases. So we're starting by talking about types of acids and bases. One type is called Arrhenius. A second type is called Bronsted-Lowry acids and bases. And then we'll talk about water and how water can act as both an acid and a base. So in an earlier chapter, we talked about electrolytes, and we'll start by reviewing what that means. So electrolytes, we said, are substances that produce ions when they're dissolved in water. And so for this entire chapter, we are going to be talking about things dissolved in water. Okay, and we said that there were varying levels of efficiency. Some things were more efficient at dissolving in water and some things were less efficient. So we'll make a bar line here. And so there were three different regions in our last definition. There was a region down here that was pretty low efficiency, a region up here that was pretty high efficiency at dissolving, and then that middle region. So this region that has pretty low efficiency at producing ions, these are called non-electrolytes. There are so few ions produced, it doesn't really count. Then we have the middle region. Those are called weak electrolytes, because some of the molecules separate into ions and some of them don't. And then over here, near 100%, we have strong electrolytes. Essentially, 100% of these molecules separate into ions when put into water. So if we were going to write a chemical reaction for this process, what would that look like? So it would look something like we have molecules of electrolyte, and we take those and we put those into water. And for some of them, they dissolve to produce some sort of aqueous ions. Okay, and anytime we can write a reaction, we can write an equilibrium constant. So our equilibrium constant, KEQ, remember from the last chapter, that's going to be products over reactants. And so in this reaction, our product is going to be the ions, and our reactant are going to be the molecules that haven't separated, the original electrolyte molecules. Okay, so now, knowing what we know about the K, let's see if we can assign a specific K value to each of these different ranges. So let's start with non-electrolytes. Non-electrolytes are the ones that are very low efficiency for this forward reaction. So most of the molecules are going to stay as molecules. Very few of them are going to be ions. So we're going to have a small number over a large number. So this number for non-electrolytes is going to be approximately 0. Okay, what about for strong electrolytes? Strong electrolytes are here near 100% efficiency dissolving into ions. So this reaction is going to go almost 100% in the forward direction. So we're going to have lots of ions and very few molecules left in their original state. So this is just going to be K equals huge, or more precisely, greater than 1. But we assume this is such a large number that we don't even bother to report it. So that means for electrolytes that are weak, the KEQ is somewhere between 0 and 1, which does not sound like a very large region, but is. Okay, So there's our definition for electrolytes. And so this chapter is about acids and bases. Acids and bases are a particular type of electrolyte. They produce ions when they're dissolved in water. So one definition for acids and bases was made by someone named Arrhenius. So according to the first definition, an Arrhenius acid is something that produces H3O plus ion when it's dissolved in water. And this is the first time we've seen this molecule. H3O plus is called hydronium. We're going to be talking about that a lot in this chapter. Okay, so let's write a reaction where we can see an acid producing H3O plus. So here's an acid that we know, hydrochloric acid. And it's going to be aqueous because it's in water. Water is a liquid. And when it's put into water, it forms H3O plus, according to the definition, and there is a chloride left. So the Arrhenius acid, that's this one. Here on the reactant side, it is the one that produces the H3O plus, and there's the H3O plus. Okay, and then if we want to use the same type of definition for a base, an Arrhenius base is one that produces hydroxide when it's dissolved in water. So we can write a reaction for an example base that fits this definition. Here's a base we should be familiar with, sodium hydroxide. When we put that into solution, it produces a sodium ion and a hydroxide ion. Okay, so the sodium hydroxide, that's the thing that produced the OH minus, that's our base. And here's the OH minus that we made. So this definition is okay. It works for a lot of acids and bases that we work with in the chemistry lab, but it doesn't work for all of them because not all bases have an OH in them. Some of them don't, but can still act as bases. So we need to make a modification to this definition so that it's more widely applicable. So you need to change lanes here. This definition doesn't always work. This definition fails for bases like NH3. Because NH3 doesn't contain hydroxide. So we need to try something else and define acids and bases a little bit differently. All right, so some new folks came along and they made a modification to the definitions of acids and bases, and they were named Bronsted-Lowry. So according to this new definition, a Bronsted acid is one that donates protons. And when we say protons, what we actually mean is a hydrogen ion. But since a hydrogen ion only has one proton, it doesn't have any neutrons in the most stable isotope, and it doesn't have any electrons, we just call it a proton most of the time. So let's draw a reaction for an example of a Bronsted acid. So NH4 plus is a Bronsted acid. And when you put it in water, it is going to form NH3 and H3O plus. Okay, so the Bronsted acid is the one that donates the proton. So this is the acid. Here it is before it donates the proton. And after it donates the proton, it becomes this one, becomes NH3. And so these two go together. One of them is before the process happens, one of them is after. So these are a pair we're going to talk about together in the future. So we're going to call this the conjugate acid-base pair. So this one is going to be the acid because it's the one that donates the proton. And after it donates the proton, we are going to call it a conjugate base. And this reaction that we wrote, where we drew the acid in water dissolving to form ions, this is called the acid ionization reaction. You want to make sure you commit this generic type of reaction to memory. Acid plus water dissolves into ions, because we are going to be writing this a lot in this chapter. Okay, moving on to the base. The Bronsted definition for a base is the opposite of an acid. It's one that accepts protons. So we'll do an example reaction for that. And we'll use the conjugate base this time, NH3. Put that in water, and it forms NH4 plus and OH minus. Okay, so this is our base, NH3. This is what it looks like before it accepts a proton. After it accepts a proton, it turns into NH4 plus. And so we're going to call NH4 plus its conjugate acid. And this is going to be another conjugate pair. Okay, and then we wrote this reaction here of a base that's put into water to form ions. And so that is going to be called the base ionization reaction. Another important one to remember. Okay, so what we've started talking about here is we started talking about conjugate acid-base pairs, how one thing forms another thing on the product side. So we can say that every acid-base reaction must contain the following. Must have an acid in the reactants, and a base also in the reactants. It's called an acid-base reaction for a reason. And it also needs to have a conjugate partner for each. Okay, so there needs to be an acid and a partner for the acid. There needs to be a base and a conjugate partner for the base. So let's revisit the one we drew up here. So this was our acid, the NH4 plus, and after it donated a proton, it became NH3. And our new definition says we need to have an acid and a base in the reactants of every acid-base reaction. So that means we need to have a base. And so water is going to be our base. And so that means that water is going to be accepting a proton. So before it accepts a proton, it looks like H2O. After it accepts a proton, it looks like H3O plus. So this is going to be the conjugate acid. And we can even track where the proton went. So that proton started here, and NH4 plus lost it, and it gave it to the water, and it ended up here, and the H3O plus. Okay, and we can do the same thing for our base reaction. So NH3 was a base, and it formed the conjugate acid NH4 plus, and so that means there needs to be an acid on the reactant side. So water is going to be our acid, meaning water is going to be donating a proton. So after it donates a proton, it has one less hydrogen. It is now an OH minus. And this is the conjugate base. So these sets are also conjugate pairs. There will be 2 conjugate pairs in every acid-base reaction. There we are. So acids and bases donating protons and accepting protons. And then the last thing I want to draw your attention to here is you might have noticed that water was acting as a base in this reaction and as an acid in this reaction, which is kind of unusual, but actually some compounds can act as an acid or as a base. And we have a word for that, and that word is amphoteric. I like to think of this as being similar to the word amphibian, where you can live on land and in the ocean. Amphoteric can be an acid and a base. So it describes a compound that can act as an acid or a base. And we'll put an exclamation point because that's cool. And water can even act as an acid or a base even when it's the only thing present in the solution. It can donate and accept protons with itself. And that is a fact we are going to exploit as we move through this section. So if we mix 2 waters together, the acid will make an H3O plus and the base will make an OH minus. And this is called the auto-ionization of water because it's ionizing itself. And we can label our conjugate pairs in this one. And it really doesn't matter which water we start with. So if this water goes from H2O to H3O plus, it's gaining a proton, accepting a proton. So that means it's going to be the base, and this one's going to be the conjugate acid. And this water over here can be paired with the OH minus, and it is losing a proton. It's donating, rather. So that makes it the acid, and its partner, the conjugate base. So we can describe acid-base reactions in terms of one reactant that's the acid and one that's the base, and we can find a pair for each of them in the products that they become after donating or accepting a proton. So in the next video, we'll talk more about acidic and basic solutions and how to use pH to describe how acidic or basic a solution is.